Hi guys, just checking in to see how today went. We are running through an airport. Here's my husband, Ron. Running through an airport. We got delayed with Snowmageddon yesterday, but I just wanted to check in, make sure you learned what you were supposed to learn today. I'm gonna append this to a little video explaining real briefly the concepts from today. Hope it went well. See you soon. Let's review what you learned for the genetic traits in this particular day. One of the ones that we learned about is sex-linked traits. So this is where, remember how we talked about autosomes? Autosomes are the other 22 pairs, and then there's the sex chromosomes, the X and the Y. And so the sex-linked traits, they're on the sex chromosomes. And so the one that you guys did in class, I think, is color blindness. And so let's do my family because it's kind of fun. So here's me, here's my husband. All right, and I am not colorblind, neither is my husband, but my father is red-green colorblind. Okay, so here's my dad. So what can you tell me about his X? So you should be able to tell me that he's got that little A on his X because he's colorblind. And so what does that mean about me? Well, think about it. It means that I'm not colorblind, so we know that I have at least a big A, but my dad only has this one X to give. And so I have that little A. So I am definitely a carrier. Now my husband is not colorblind. So what do we know about him? Well, we know he's carrying a big A, and then he doesn't have another X chromosome, right? So what are the chances that our kids will be colorblind? Well, consider the fact that all of my kids are boys, right? So Tag, Cash, Gage, Emmett. So knowing that they're boys, we automatically know that they got the Y from my husband. So that means the X that they got from me, it's a 50-50 chance, right? So we'll start at the bottom here. Emmett is not colorblind. Gage is not colorblind. Cash is not colorblind. Tag, or kid, is colorblind. So we beat the odds, so that's kind of great. Okay, so that was the first inheritance pattern you learned about. The second one is not an inheritance pattern, it's just a phenomenon that we talk about. And so it's called gene linkage. And it's pretty common, right? If you think about it, we only have 23 pairs of chromosomes, but we have hundreds of thousands of genes. So the chances that two genes are on the same chromosome is pretty common, right? And so if they weren't linked, let's say we're looking at two genes, for instance. Let's say we're looking at the gene for coat color, and you can either be black or you can be gray, let's say. And then we're looking for another gene. Let's say this is for whether or not you have spikes. I have no idea what this organism is. But we'll do, oh, spikes is a terrible one because S. Spikes, no spikes, right? So if these genes were truly independent, then you could give this chromosome and be this. You could give this one and be that. You could be little b, big S. You could be little b, little s, right? So those are the four possible sperm, for instance, that person could make, okay? And then you would expect, lots of variety in the offspring. But if instead they're actually on the same chromosome, let me draw that again, where we have our big B and our big S. Now, it doesn't always have to be the dominant with the dominant and the recessive with the recessive. It could be linked the other way, but in this case, we're going to make it dominant recessive like that. So in this case, we could get this sperm right here. So we still get that one, because that would be if we got that chromosome, right? And then we could get this sperm here if we grabbed that chromosome. Little b, little s, right? So those are the two that we could get. We can't get these middle two unless you get some kind of crossover event where the two chromosomes like flop, the top halves flop. And so in this case, you'd have that big S here and little s here, but then the B's have swapped places. And in those cases, you can get these two sperm types. These are called recombinants, because they result from a recombination of two chromosomes. And so if a gene is linked, you get less when you're doing like that big Punnett square, you get less of these people in the middle, where you had recombination, and the closer the chromosome or the genes are on the chromosomes, like let's say that the B and the S were like this on the chromosome, then the chances of getting a crossover right there is much lower than if they're all the way anywhere in between, you know? And so the distance will tell you how many recombinants you get. And so we can look at a recombinant frequency and we can tell approximately how far apart the genes are on the same chromosome, depending on how often they separate from one another when making gametes. And so I think there's a problem on one of your homeworks maybe where you build a recombinant map, right? So if they cross over 100% of the time, then they're probably really far apart on the chromosome. But if they only cross over 50% of the time, then they're probably more like that far apart. If they only cross over 10% of the time, then they're probably really close together. And you can figure out the order of genes on a chromosome. Okay, the last thing we did were pedigrees. So a pedigree is just a way to show a particular trait. And so on a pedigree, the rules are if you have a square, it's a boy. If you have a circle, it's a girl. If there's a line in between, it just means that they mated with each other. Oops, where's my little thing? Right, so these two mated with each other. And then coming out here, these are children of them, right? And then the other rule is if it's filled in, it's showing whatever trait you are mapping. So it could be a dominant trait, it could be a recessive trait, we don't know. And so in this case, sometimes you can tell. So in this particular, the way that I've drawn it here, let's ask ourselves, could this be a recessive trait? If it's a recessive trait, then those people that are colored in have to be little a, right? If it's a recessive trait. So this person has to be little a, this person has to be little a. And so to get this child right, to get this child right here from a parent who's this, it means that the other parent also had to have that little a, right? So this parent has to be a heterozygote in order to pass that on. And same thing, actually here we don't, in this particular one we don't know, right? Because none of the kids have it. So this person could be heterozygous and they've just beat the odds, or this person could be homozygous dominant. All right, so we couldn't tell. So this one could be recessive, but let's just do it in a different color. What if it was a dominant trait? If it was a dominant trait, then instead of being this, then to not have the trait, they have to be homozygous recessive. So everybody who's not filled in has to be homozygous recessive, right? So is this still possible? Well, then this person has to be what? They've got a child with it, which is not that, right? We've got a child with it and a child without it. These two children, you can see children with it, or children with it, children without it. So they definitely have little a's, so that means that this individual here has to be big A, little a, and so they donated the little a to this child, they donated the big A to this child. So this child would be big A, little a. So in this pedigree, you can't tell whether it's dominant or recessive. But let me fill in, let's say that this couple, let me show you this couple right here. Let's say that they have a child with the trait. Automatically you have to rule out, oh crap, they can't be this, right? They have to be carriers so that this offspring has it. And so if this were the case, then you'd have to say, oh, this must be tracking a recessive trait. Okay, so you should be able to do it by a process of elimination. Try both out and see which one works and follow it all the way down all the generations. So hopefully that helps. I think that's it for this day. I hope you're enjoying class. Dr. St. Clair's awesome. See you soon.